Okay, we can always come back and catch them later, but figured I'd start with that. So if anybody has any, 1 through 40 from the homework.
I think I have questions, but I need to look.
Okay. Well, while you're waiting, we'll ask Eva if she seemed like she was going to ask about them too. So what do you got there, Eves?
The only two problems that I had out of all of them was 37 and 38. I wasn't 100% sure on how to do that.
Oh, okay. So let's do one of the two. And these are just both kind of a hassle because they're just involve a little bit of work. But do you have a preference on 37 or 38?
37 I mildly got, but like some of the sides, it just didn't really make sense. But 38 I was just stuck at, so I would prefer to do 38.
Sure. So I'm going to just sketch a quick picture, and now I'm not going to bother to like super plot these things. I'm just going to kind of ish put where they'd be at.
It's supposed to be up there right now.
Oh.
Sorry.
That's okay. I probably moved it because I was doing something else. You're welcome. Okay, so here is our points, x, y, and z. What I'm going to do is I'm going to translate these into vectors. So the vector xy is going to be y minus x, and then y minus x, and then we have yz, which is going to be z minus y, and then z minus y, okay, and then which is going to be x minus z, and then x minus z, okay, so the length of xy is just going to be this, which is 36 plus 25, which is 61. Let's see, that's 169 plus 121, so that's 170 and 120, so 390. No, 290. Excuse me. And then we have -7 squared plus -6 squared. That's 49 and 36, which is 85. So far, so good? Okay. And now what I'm going to do is I'm going to use the angle between two vectors theorem to find the angles for these. So I'm going to call, so for example, if we have the angle, let's see, we'll say angle x, y, z, which is this angle here. We'd actually need to do is going to be between the vector yz and the vector yx. Notice that we don't have yx on here, but we have xy. So yx should just be the opposite order, so positive 6 and positive 5, because it's just going the opposite direction. Right, it just would be this. Okay, so then I'm going to use my formula, which you can find on page 7 of the notes, that says that this theta is equal to the cosine inverse of yz dot yx over the magnitude of yz times the magnitude of yx. So yz dot yx is going to be negative 6 times positive 6, so negative 36 plus, oops, no, yz is that one, so 13 times 6, which is 78, and then 11 plus 5, or 11 times 5 is 55, over yx, which is still square root 69 or 61, and then yz, which is square root 290, and then we'll go to our calculator. So I have 78 plus 55 over square root 61 times square root 290. And that is in degrees. So that's about 0.43 degrees. And then you do the other two angles similarly, right? It's just a lot of work to get it all. You're okay with what we did though?
Yes.
Okay.
That does make sense.
Okay. Tests. Of course. Sarah?
Yeah. Okay, I had a question on, it's like on page 3 of the lesson. So when you're trying to find like the direct angle to a point and you use like inverse tangent, like I don't know if this went over this, but the points, if they're negative, are they like absolute value or do you?
Okay. So let's say we want to find so like you're asking for something like this, right, Sarah?
Yeah.
Okay. So what we're doing is we're looking for this angle here is our theta, right?
Yeah.
So what I would say is I'm going to, the way I like to do this anyways, which may not be the same way Mr. Stan did it, the way I like to think about this is I'm going to find this angle phi and think about theta then as 180 plus phi. Because this part is 180 and then we add that much more. Okay with that?
Mm-hmm.
So I'm always going to draw the picture because without the picture I don't know whether I should be adding or subtracting. I don't know if I should be using 90 or 180 or 270 or 360 or whatever. Is that okay?
Yeah.
Okay. So the reason I like to do that is that phi is always going to be the tan inverse of the absolute value of y over the absolute value of x.
Okay.
So that's why I like to do it this way, because I don't ever have to think about whether I need the negatives or not.
Mm-hmm.
I'm never going to use the negatives because I'm going to rely on the picture to make sure I'm in the right quadrant.
Okay.
Does that feel okay?
Mm-hmm.
You're welcome. That's what I think is the easiest way to think about it anyways. So when I do it, I always use the absolute values because I'm going to draw the picture and then use that to figure out what quadrant I'm in. There's other ways to do it, but I think they all require more thought than looking. The picture I like because I'm like, okay, that's the right angle. Without the picture, I could get an answer and be like, I don't know. You know. Anyways. Cool. Easy enough, I guess. Who's next? Anyone else? Is the temperature starting to improve? Good. I don't know why it does that. Sometimes when I'm in here by myself, I think without the lights on, the heat kicks off. Amanda.
Could you please do number 26?
Sure. Okay. So it wants this to prove this. Okay. Okay. So I'll start by doing that, and I'm just going to define U1, U as U1, U2, V as V1, V2, and W as W1, W2, which is just like our component form definition of a vector, right? No big deal there. So I'm going to work on the left-hand side and try to make it equal to the right-hand side. So it's not as well regarded and approved to work on both sides and try to meet in the middle, although like from a style perspective, that's not great, but I guess it's okay. But I'm rather just going to work on one side and get to the other side, which is sometimes a little bit trickier, but is a little bit more rigorous. So I'm going to start just by these vectors with their component forms. So far, so good. Okay. And then I'm going to do the part in the parentheses first. Add two vectors in component form. We just add them component-wise. And now I'm going to do the dot product. Oops. So when I do the dot product, we multiply the components together and then add them, right? Still doing good? Okay. So I'll distribute things through. So I have U1 V1 plus U1 W1 plus U2 V2 plus U2. Is all over these places? And I'm going to reorganize things now. So I want to get the V's together in one place. And I want to get the U's or the W's together. So I'm going to kind of group them together that way. Still with me okay there, Amanda? Yeah. Okay. And if I look at this piece now, the U1 V1 plus U2 V2, that is by definition the dot product of, and the other one is by definition the dot product of, oops. Oh yeah, I did, sorry. U and W, right? which is what I wanted to get to. Is that okay there? Yeah, so the only tricky part was to this step in realizing how you need to group the pieces together so you can get those dot products that fall back out. You're welcome. Who's next? Oakley dokley. On to new things then, I suppose, right? So in section 8.3, we're going to be talking about applications of vectors. So one application we've already kind of looked at in a previous chapter, and that was kind of doing some of these navigational story problems. So we'll do another one of those just for an example. But I think we did this back in chapter 4. And then we'll extend this idea. We'll define another vector operation and talk about some story problems that use in that sense, in that context. So here we have that a boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So really we have 2 legs on this journey. So 40 knots. And then our second leg is 55 knots of 162 degrees. So remember, for bearings, we calculate a bearing differently than we calculate a standard position angle, right? First thing I want to do is translate those bearings into standard position angles. So I'm going to draw the bearing first. So bearings always start at due north, and they rotate clockwise. So 215 degree bearing is like here. So this was, and 35 more would make 215. To get my standard position angle, I'm doing this. So that's 90. That's 90, and then the complement of 35 is 55. So my standard position angle, which I'm going to call theta, is 90 plus 90 plus. So we're like somewhere over here. So that was 9, and then 72. My standard position angle then is 90, 90, 90, and the complement of 72, which is, so that's going to be, everybody so far so good on that. Okay. And my magnitude then, it's just going to be the total distance I traveled. So 40 times 2 is going to be 80 nautical. Times 55 is going to be 165 nautical miles. And now I'm going to resolve these vectors into component form. So I'm going to call this vector L1. So that's going to be 80 times the cosine of 235, and then comma 80 sine 235. And then similarly, leg then is going to represent vector L1 plus vector L2. So when I type in 80 cosine 235 plus 165 cosine 288, I get about 5.10. And when I do 80 sine 235 plus 165 sine 288, I get about 222.46. Everybody's okay there? So I just typed that into my calculator. I just didn't show me doing it. Okay. So my magnitude of t is going to be just doing that. So I get about 222.51 nautical miles. And my theta then, that will make things a little bit easier. So I'll plot my angle. So I go 5 over and 222 down. So there's my vector t. And what I need to do is I need to find this bearing. Piece is 90. And I'm going to call this other part phi, which is just going to of the absolute value of 46, which comes out to be about 88.69. So
instead of using like what you just did, or like instead of using the vectors, can we just like solve the triangles?
Well, here's the issue: is that this is in the vectors chapter. So the point of this is to like get comfortable using vectors to do it.
Okay, that makes sense.
So like, sure, but you're going to have a non-right triangle that you're going to have to solve. So you'd have to use the law of sines and cosines and possibly run into ambiguous cases and all kinds of things. That would not be perhaps the simplest route all the time. The nice part about this method is it doesn't really change. It's the exact same every single time, regardless of what the two vectors are doing. But yes, I mean, to answer your question, you can do it that way. I would ask you not to do it that way in this chapter, though. You know what I mean?
Yeah.
Okay. Okay. So that's just like a recapping of something we've already done, right? We've been looking at doing them in a different set of tools. So a new vector operation that we'll talk about right now is called the projection. So let's say we have this vector u and this vector v. What I can do here is, or what is often going to be valuable in a real world situation, is if I draw a line perpendicular from w to v, and then I talk about the vector formed on v to that point, we call that vector the projection of u onto v. So the v is a subscript, and the u is like the argument. And we can call this vector over here, did a poor job of drawing that, very WE. This vector W. And what is special about the relationship between U, W, and the projection of V onto W? Well, here's the big peak, or the big takeaway here. So if we talk about, I should have used green. I should use green. I should use blue. If we talk about W as this vector here, W and the projection of V onto U are orthogonal. What does that mean again? That they meet at a right angle. And we know that then W plus the projection of V onto U is equal to U. If you look at the way we've drawn that picture, that's just our definition of vector addition, right? Because we've drawn them head to tail. Everybody's okay with that idea? So what becomes important to us then is how do we calculate that projection? Well, there's a formula, which is lovely, right? We love formulas. So the projection of U onto V is U dot V divided by the magnitude of V squared times vector V. Worth pointing out to you here that this piece here, this is a scalar, right? The dot product of two vectors gives you a scalar, just a real number. And the magnitude of a vector is a scalar, just a real number. So this is just like a scalar multiplication, which should make sense to you, because what is the projection of U onto V really? It's just shrinking at some scale of V, right? It's in the same direction as V. It just gotten shorter or longer, I guess, in some case. Does that make sense? From the picture, hopefully that feels intuitive. What else should we observe? There's another important observation here. Let's use a green one here. I said green one. That's still not green. Trying to color code things. Okay, so if we look at this picture that we've just drawn here, does the length of V really matter? Would I end up with like the same picture if like I drew V like that? Not really, right? I mean, we'd still, right? Does everybody kind of see that? Really what V is contributing is only a direction. So in the abstract, the magnitude of v doesn't really matter, right? What we really need is just the direction of v. So unless the magnitude of v is specified or implied somehow, we can really just assume that magnitude of v to be 1. And it's going to be fine. And that'll be something that'll come up in these story problems that we're going to look at here in a moment. But before we do that, oops. Okay, so our example here, we're going to find the projection of u onto v and then express u as the sum of two orthogonal vectors. So my formula, the projection of u onto v, is going to be u dot v over the magnitude of v squared times v. So u dot v is going to be 31.6 negative 4, which is 3 times 6 plus 1 times negative 4, 18 minus 4, or 14. V squared is going to be 6 squared plus negative 4 squared. So that's 36 plus 16, which is 52. So we can say this is then 14 over 52 times 6 negative 4. Now 14 over 52 we can really reduce, right? Let's call that 7 over 26 just to make our lives a little bit easier. I'm going to write it that way though so it's clear where the 14 and 52 came from. Because if I just wrote 7 and 26 there and you went back and looked at it, it'd be like, where in the devil did 7 and 26 come from? So I don't see those other two numbers anywhere in the problem. So I know it seems stupid that I wrote it down and crossed it out, but I did it that way because if you go back and look at the notes, like, where the heck did 7 and 26 come from? All right, so that's going to give me 42 over 26. Well, yeah, I might as well write it that way. We'll reduce again. And then negative 28 over 26. And that will reduce down to 21 over 13 and negative 14 over 13. Everybody good with that? So that's the first part. So far, so good? Okay. And then I know from the picture above that we said W plus the projection of U onto V equals U. So the vector that we're missing is W. So I can solve for that by just subtracting the projection of V onto U from both sides. So making a common denominator, 3 is the same thing as 39/13. And 21 minus 39 is 18/13. And then 1 minus a negative 14/13 is 13/13 plus 14/13, which is 27/13. So I can say then U is that's my projection of U onto V plus that vector W Is everybody okay there? Again, I kind of overdid it maybe on the work shown. You probably don't need to show all the work that I did there, but again, these are notes. So I try to overdo it on these situations because if you're going back and looking at things, it doesn't help you if I have like the minimum amount of work shown. And you're like, wait a minute, how did he do that? So again, maybe I overdid it here or there with what I wrote down, and you're like, geez, so Pete's, I'm not ever going to write all this stuff down. It's like, maybe you don't have to. Like, I wrote a lot of stuff there that maybe not all of it's super duper necessary. So let's do a couple of example story problems now that utilize this idea of a vector projection. Those of you in physics class right now, the way these problems are worded should sound kind of familiar. You've probably gotten to this point by now. Let's make that font a little bigger, huh? Kyle is going sledding down a hill with an angle of 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? Okay. So I'm going to start by just drawing a picture of the situation. So there's my hill. God bless you. And we know there's a 25-degree angle of incline. So the 25-degree angle is that piece there, right? Which means that this is also a 25-degree angle there. And this piece is then a 65-degree angle there. So far, so good? Okay. Now, Kyle and the sled's force is due only to gravity. What direction does gravity move us? Straight, right? So I'm going to call that vector G. Guess I should have done some color coding here. I'm going to recolor that as a different color. I'll call that vector H for the hill. And what we're looking for then is this piece, which is the projection of G onto the hill. Everybody so far so good? Okay. So I'm going to resolve these into component form vectors. G is really easy, right? Since you're just pointing straight down. Everybody's okay with that? I don't have to justify that at all. Okay. I mean, if you wanted to call the angle then 270, you could do 270 and do 165 cosine 270, 165 or sine 270. But like, boy, that seems like a lot of overkill to me. For the hill then, that's our angle theta. So 360 minus 25 is going to be 335. So my H is going to be, do we know how long the hill is? Nope. Does it matter? Nope. Why not? Because it's the vector we're projecting onto, so all we really need out of that is the direction. So we're just going to assume the magnitude of H is 1. So our H is really just 1 cosine 335, 1 sine 335. Everybody cool there? Okay. So if we go ahead and find our projection now. Oops, I should have done that one in blue, huh? Oh well. I wonder, can I do that? Can I change the color just by doing this and then like picking it to be blue? No. Darn it. Anyways, you guys will just have to deal with it. So we need the projection of G onto H. Okay. So projection of G onto H is just going to be 0 plus negative 165 sine 235, or I'm sorry, 335. And the magnitude of H is just going to be 1, as we said earlier. So when we plug this in, we have just negative 165 sine 335. If you want to turn that into a decimal, you could have. I'm just not interested in doing that. Then cosine 35 sine. Again, you could turn those into decimals if you wanted to. I'm just not interested in doing it because it's a little bit more instructive if I just leave whatever was in there. You know what I mean? And when I type that gobbledygook into my calculator, I get 63.20, comma, negative 29.47. So that's my vector for the projection. The problem asks for how much force is directed down the hill. So that's the vector of the force going down the hill. What we really want, though, is the magnitude of that vector. Which is about 69.73 pounds down the hill. How many of us are in a physics class that have done this kind of a calculation before? handful of us. This looks familiar though, right? Does this seem a little bit easier of an approach than like the weird tilting axis crapola that you have to do in your physics class to make that work? About the same. I think that this is a little bit more idiot proof because it doesn't rely on like drawing a good picture and building a good diagram. I always had a devil of a time in my physics class getting the pictures to work out right.
Mr. Kulik?
Yes, sir.
So at the very end, how did you get it into magnitude? The last step.
Oh, I just did like the x squared plus y squared square rooted.
Okay.
Okay. We'll do one more example here, and then we'll call it good for today. How's that sound to you guys? Mostly because, well, these story problems are kind of hard, and they take a little bit of time to process, and I don't want to overload you guys. Make it a little bigger than that even. All right. So we have a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assume the crate is of negligible weight. What is the amount of force directed up the ramp? Okay. I'm going to start by just kind of drawing my picture. So here's my vector r for ramp. So it should be easy to see that the angle for r is going to be 40 degrees, and the magnitude of r is going to be 100. Oops. I don't mean that to be r. This is the crate. My goodness gracious. Because it's saying that the crate is being pulled. My goodness gracious. Okay. And then we have our ramp, which is like it said, what is it? 10 feet horizontally and 2 feet vertically, right? Oops. So R is clearly just the component form 10-2. Everybody's okay there? Okay. And maybe I drew a kind of a crummy picture there, but it's fine, whatever. What we want is the projection of C onto R. Well, to get C, first we have to get that into component form. So 100 cosine 40, comma 100 sine 40. And we just have R dot C over magnitude of R squared times R. Now in this case, R has length to it, right? You can't just assume R to be 1 because R has some actual dimension given. Everybody see the difference between this problem and the previous one, where we had no clue how long that hill was before, but here we have a definitive how long r is. So you have two options here. We can either use r as the component form here, where we actually have to calculate the magnitude, or we could figure out the direction of r and use that with the magnitude being 1. I think it's always much easier just to, if we have r in component form, just use it in component form, than it is to like translate it into its unit vector in the same direction and use that. That to me feels like more work than to just use the formula the way it is. But you could do that. It's not wrong to do that. Is everybody still okay? But you can't just assume this r is 1. You'd have to make r 1 by calculating its unit vector. But I don't think that's going to be pleasant. So r dot c 10 comma 2 dot b comma 100 sine 40. When we do that in our calculator, I didn't even bother to do it, huh? And then this is going to be 104. So when I do this, let's see, 10 times that is 1,000 cosine 40, plus 2 times that is 200 sine 40, and then over 104. Sorry, that's getting pretty messy over there, 40. And then the vector 10, 2. And when I type all that gobbledygook into my calculator, I get 86.0 comma 17.2. And then for my answer, the projection of C onto R, we want the magnitude of that. Which is about 87.72 pounds up the ramp. Yeah. Before we start talking about vector equations and stuff, we should probably stop here. 20 minutes isn't enough to get into that junk. Besides, those story problems are typically not super duper easy. So at this point, you guys should be able to do 41 through, or sorry, 41 through 50. Just let me double check and look at that worksheet on what we have there. Nope, that is not yet.
That is not a worksheet.
That worksheet we're not ready for. We need to do the next couple of sections.
Okay.
And this obviously will be part of Sunday's homework check here.
I'm going to finish the last one.
Yep. Cool. Questions for me, you guys? Alrighty. Those of you that are working from home, you are free to go. So if you want to peace out and get to start on your homework, that's cool. Bye-bye. If you don't, and you want to stick around, that's cool too. But they all left, so I guess they did want to leave.